Professor Dave and Chegg here. We've seen how hybrid orbitals can explain many aspects of chemical bonding and molecular geometry. But there are areas in which this model breaks down, and there are phenomena it can't explain. To get a more thorough understanding of chemical bonding, we will have to examine something called molecular orbital theory. This theory can get quite daunting, but let's just look at the very basics to get an introduction.
Unlike valence bond theory, which is the theory that uses hybrid orbitals which are specific to one atom, molecular orbital theory combines atomic orbitals to produce molecular orbitals that are delocalized around the entire molecule rather than belonging to the two atoms in the covalent bond. Let's look at this table to compare the assumptions involved in the two theories. The first difference is that valence bond theory considers covalent bonds to be localized between a pair of atoms. MO theory sees them as containing electrons that are delocalized throughout the molecule in molecular orbitals with quantized energies. One theory uses hybrid orbitals, the other does not. One theory forms sigma and pi bonds, whereas the other generates bonding and antibonding interactions based on which orbitals are filled, and one is concerned with molecular shape while the other is not. We will find that molecular orbital theory is useful in explaining many phenomena that valence bond theory simply can't, and though we won't cover all the ways in which this theory has utility in this tutorial, let's just get a sense of how these orbitals are constructed and represented on diagrams. First off, we need to look at the way that MO theory combines atomic orbitals to produce molecular orbitals. This is done through a mathematical process called the linear combination of atomic orbitals. We know that each electron can be described by a wave function. When we combine two waves, they can either line up so as to give constructive interference, where the peaks and troughs double to give a wave with up to twice the amplitude, or they can give destructive interference, where every point on the wave cancels with the point on the other wave to give a wave with as little as zero amplitude. This applies to orbitals because electrons are three-dimensional waves that combine with in-phase waves to produce a region with a high probability of electron density, as well as out-of-phase waves producing regions of no electron density, which we call nodes. When the two 1s orbitals from two hydrogen atoms overlap to form a hydrogen molecule, they will produce two molecular orbitals. The in-phase combination produces a lower energy sigma s bonding orbital. The out-of-phase combination, which essentially subtracts the wave functions, produces a higher energy sigma s star antibonding orbital, which has a node between the nuclei. Electrons will occupy the lowest energy orbital available, which is why the two electrons in this bond will reside in the bonding orbital. Looking at p orbitals, each p orbital has two lobes with opposite phases. When lobes of the same phase overlap, which here are represented by the same color, we get constructive interference, which makes a larger region of probability density. When lobes of opposite phase overlap, it's destructive interference, and we get a node and an antibonding orbital. If these overlaps occur on the x-axis, these would be the sigma px and the sigma px star orbitals, which will be bonding and antibonding respectively. If two p orbitals have lateral overlap rather than direct overlap, they generate pi orbitals. If they overlap in phase, it's the pi orbital, which is a bonding orbital. The node will be on the internuclear axis. If they overlap out of phase, it's the pi star orbital, which is an antibonding orbital. The node will be between the nuclei, meaning electrons cannot be shared between them. Now that we have introduced the different shapes of the molecular orbitals, as well as how they are formed, we want to understand their relative energies so that we know which orbitals will be occupied. To do this, we must learn how to draw molecular orbital diagrams. Let's look at an orbital diagram for a diatomic molecule like the Be2 cation, which will involve a neutral beryllium and a beryllium with a +1 charge. The molecular orbital diagram will always show the atomic orbitals of one atom on the left and the atomic orbitals of the other atom on the right. In the middle, we see the molecular orbitals that are produced by the two atoms when their atomic orbitals overlap in different ways. The lines on this diagram are just like the ones on an orbital diagram for an individual atom. They each represent one orbital, which can hold 2 electrons, and the molecular orbitals will be filled according to the Aufbau principle, meaning from lowest energy to highest energy, and following Hund's rule, meaning for a set of degenerate orbitals, which are orbitals that are of equal energy, we will place 1 electron in each orbital before doubling them up. For each pair of orbitals that combine, we get 1 bonding orbital and 1 antibonding orbital, so the number of orbitals is conserved. To fill up the molecular orbitals, we simply take the electrons from the atomic orbitals and fill up the molecular orbitals starting from the lowest energy. We have a total of 3 valence electrons from the 2 atoms that need to go somewhere, so we put 2 in the sigma 2s since that's the lowest energy orbital, and once that's full, the remaining electron will go in the sigma 2s star, which is the antibonding orbital. Let's look at another one with more electrons, like an oxygen molecule. On each side, we place an oxygen atom with all of its valence electrons. The 2s electrons go and fill up the sigma 2s bonding and antibonding orbitals, and then the 2p electrons fill up the next set of molecular orbitals as shown. When we look at a molecular orbital diagram that has been filled in to show the orbitals that are occupied by electrons, we can use this information to calculate the bond order for a molecule. This is done by comparing the number of electrons inhabiting bonding orbitals, orbitals which increase the bond strength, and the number of electrons inhabiting antibonding orbitals, orbitals which decrease the bond strength. The way bond order corresponds to our understanding of molecules is that it dictates the number of pairs of bonding electrons between 2 atoms. So a bond order of 1 corresponds to a single bond, a bond order of 2 corresponds to a double bond, and a bond order of 3 corresponds to a triple bond. To calculate the bond order, we simply take the number of electrons in bonding orbitals, subtract the number of electrons in antibonding orbitals, and divide the result by 2. The bond order will tell us the strength of the bond between 2 atoms, as a higher bond order means more bonds and therefore a stronger interaction. Let's go back to our orbital diagram for the oxygen molecule. We can see that there are 8 electrons in bonding orbitals, and there are 4 electrons in antibonding orbitals, which are the ones with the stars. Let's plug those into the equation and see that we get a bond order of 2, which corresponds to a double bond for an oxygen molecule. There can be situations where there is a bond order between 2 integers, which would tell us that there are partial bonds present, such as is the case for molecules that have multiple resonance forms. And if the bond order is 0, that means a stable bond between the 2 atoms will not form.
So molecular orbital diagrams can tell us a lot about a molecule, including the strength of the bond between 2 atoms, which is dictated by the bond order. If all this seems confusing, don't worry. This is one of the most abstract concepts in introductory chemistry, and we don't have to have a sophisticated comprehension of it. As long as we understand just a bit about MO diagrams and can calculate bond order, we should be just fine. Professor Dave for Chegg. See you next time.